there is no one-to-one correspondence between the time constants and the poles. So if you have like 5 time constants, it doesn't mean that you have 5 poles. And even if you have like 2 poles and you know to have 2 time constants, it doesn't necessarily mean that those 2 time constants are the same as the 2 poles. And that's another one of the mistakes that a lot of people make. That they associate a pole with a node, which you can't generally do. We will see when you can do it. The poles have to be, the time constants have to be decoupled or uncoupled, but we'll talk about it. But anyhow, so now for a first order system though, there's only one pole and there's only one time constant, so they're related to simple relation. And the 0 is minus 1 over tau times h0 over h1. Right? So what can I say about the position of my 0? 0 is simply, so if I divide this by that, I can say z over p is h naught over h1. And of course you can derive this, and again the mnemonic device I used is that this is a 0, this is a 0. So 0 by something is h0 by something. Again, I mean you can always derive it again. So that tells you that the relationship between the 0 and the pole is really determined by the ratio of h naught over h1. Where they are with respect to each other. Now, you remember like a few minutes ago I said, okay, I could tell you that I have a left half plane 0 when the polarities of the two were the same. Right? For instance, in the case of an emitter follower. What did I say? I said, you know, h1 and h0 have the same polarity. So it's a left half plane 0 because I knew it would have a left half plane pole. It was a stable system. If it were an unstable system, I would have right half plane. So since it's a stable system to begin with, so my pole is left half plane, so my 0 is in the same half plane. So when the polarity of these two are the same, then the two are in the same half plane, and if it's a stable system, then it means that you have a left half plane 0. And if the polarity is different, like the case of a common source, where h1 and h0 had 2 different polarities up there, one was positive, one was negative, what happens is that you had one pole, well, the 0 is right half plane. Now you can say even more by looking at it. You can say where they are with respect to each other, which one happens first, by the relative magnitudes of these. Right? So we can actually form a little table. And the table is basically looks, I mean, it's in your handouts. So when you see the table, I just want to be consistent with what you have there. Okay. So first you can look at the polarity. You can say h naught over h1. So the polarity is here. H naught over h1 greater than 0, and h naught over h1 smaller than 0. And this is basically when the magnitude, the relative magnitude of the two is smaller than 1, which means that h1 is greater than h0 magnitude. And this is basically when h naught over h1 is greater than. Now, I don't expect you to memorize a table. I would like you to see how we arrive at these results and how we arrive at this. So if you remember this, even if you don't remember it, you can extract it from this. Right? Quickly. But how we can look at this ratio and determine where the poles and zeros are. And come up with rules of thumb. So if they are the same polarity, what do we know? If they are both of them are, so the ratio is greater than 0 means that they are in the same polarity. So it means that they are in the same half plane. This means that they are in different half-planes, of course. Now, how about the impact of the magnitude? If the 0 value transfer constant is smaller than the infinite value transfer constant, what does it tell you? Well, if this is smaller than that, it means that your 0 is smaller than your pole. Your 0 happens first. It's a lower frequency thing. So it means one way to write it is that basically you can say the magnitude of the 0 is smaller than the magnitude of the pole. Obvious, right? So this means that the magnitude of the 0 is greater than the magnitude of the pole, which means that it happens later. So, for instance, in the case of a common source, let's go back to the common source for a second. We don't even need to look at the equations, right? This state has gain. This was what we had. Now, if you do this, you kill the gain. Gain is dropped. So you know your H1 is much smaller than your H0. So it means that your 0 happens much later than your pole. And you know, you see the polarity changes because before it was inverting, and then when I short this C mu becomes not inverting. So I know I have a right half plane 0 that happens later, and much later than the pole. And there, in the case of the common drain or source follower, I know that when I see that when I short it, I have the same polarity. The polarity doesn't change, and their relative magnitude really depends on R1 and Rm. So if R1 and Rm are comparable, for instance, then I know that they're close to each other, the pole and my 0. And which one happens first will be a function of which one is bigger, R1 or Rm. So that's why both these scenarios can happen. So you can tell that by looking at it. Now, the other thing that's interesting is the time domain response of this, and frequency. So you can do a frequency domain and time domain response in parallel. And you have pictures of those in your handouts. What happens? You know, if you have a pool first, 0 first, one goes up, one goes down, depending on the phase. So it's just. Now, let's look at the time domain response. Now, to do the time domain response, what you really need to know is the following. You can actually do a decomposition of, again, that expression that we use. So I can write it as sum of the two parts. This part and this part, which I can write in the following form. Agree? So I kept this first part, so H0 over this, and this second part is H1 times this, and then I divided the numerator and denominator by tau s, so I get this. Now you can see this is a pole, and this is an inverse pole. So I can write this as two parallel systems. I can view this as two parallel systems, one with a pole and one with an inverse pole, both with the same time constant. And you know what the response of the pole is and what the response of the inverse pole is, right? Pole, so this is the single pole, so it does that, and then the inverse pole does this. Now, the question is, what is the time response of this thing? Of course, it's the inverse Laplace transform. So if I were to ask you, for instance, for the step response, S of t would be S1 of t plus S2 of t, where S1 of t is the step response of that, plus S2 of t is the step response of that. So what is the step response of a system with a single pole? Right? Time domain step response. Something like this, right? It starts from 0, and the time constant tau, it arrives at what final value? 1. So it becomes H0. And then, so this is S1. And then I have the step response of the system with the inverse pole. What is the step response of a system with the inverse pole? It's like this. So it starts with at H1 and it goes to 0 asymptotically. And this asymptotically reaches H0 with the same time constant tau. So what is the overall response of this system? The overall response of this system is a system that starts from H1 and then asymptotically ends at H0. This is the step response. Now, depending on the relative values of H1 and H0, this could look different. So let's look at 4 different cases. First one, let's assume that, so we go through 4 different ones. So let's start from the case where H0 over H1 is smaller than -1. It's a negative case, what happens is that it means that H0 is smaller than H0 is greater than H1 magnitude. So the final value is somewhere here, just H0, and they have opposite polarities. So you have your step system comes, your step response looks like this. So you go down to H1, and then you come back up to H0. You have an undershoot. This is called an undershoot. You get a first order system, right? You don't even have a second order system. And then, so this is one case. Then the other case, basically, let's go to the next range. If H0 over H1 was greater than -1, but still negative, so that means that your H1 has a large magnitude with respect to H0. So what it means is that you still get an undershoot, but it goes farther down. So that looks fun. Looks like that. So this is H1. This is H0. So you still get undershoot. Now, in both cases, whenever H0 and H1, so both of these are the two cases where they have opposite polarities, right? Which means that you have right half plane full. Right half plane 0, I'm saying. Right half plane 0. Correct? So if you have right half, so you can see, this is, you may have heard this, but undershoot is, in time domain undershoot, is a telltale sign of the right half plane 0. If your time domain response shows undershoot, it means that you have right half plane 0 in your transfer function. See? Because it only happens, you see, for the cases where, we've shown it for first order system here actually, but you see that for first order system, you have an undershoot where you have the right half plane 0, where the polarity of the pole and 0 are different. Now, how about the rest of the range? So let's go to the next, there are 4 regions, right? Which corresponds to the 4 quadrants of that table. So this is basically when it becomes greater than 0, smaller than 1. So now they have the same polarity. But what this means is that H1 is greater than H0. So it looks like this. So you start at H1 and go to H0. So you go to H1 and then you end up at H0. So you have an overshoot. By the way, you don't need a second order system to have overshoot or undershoot. You need a first order system doesn't flow. And then the final range, I guess, final segment would be when H0 and H0 is greater than H1. For instance, this was happening in the case of our common source, right? Or H0 is greater than H1 and oh no, I'm sorry, this is not the case of common source, because the case of common source is when it's this one, because they have opposite polarity. But this can happen in the case of, for instance, the source follower, depending on the right values of R1 or R0. So in this case, you have an instantaneous jump to H1, and then you go to H0. And these are on your handout. So
in the first 2 negative cases, don't you have also a second version of that?
Which is upside down?
Yeah.
Yeah, I mean, yeah, I just basically kept the
Sure.
absolute value of the, yes,
Absolute value.
You could look at this like this, right? Which is, and what would you call that? Right? It's still an undershoot, by the way. So this is another way to, so this is actually a good point. You may see this, and you may not recognize an undershoot immediately. An undershoot means going in the opposite direction of your final value initially. It may go up, depending on what polarity you have. They're both undershoots. Okay. So these 4 actually give you a way of looking at getting a sense from the time domain response of things. Any questions on this? Bless you. So now let's continue our discussion about the Miller capacitance and Miller distance. So what we did here actually magnified by that, right? So how is that? So let's say I wanted to see what does the impedance from the input look like. Because the impedance looking into here is of course infinity, right? We said that this current is 0, the impedance looking into here is infinity. So this is an ideal answer. But I want to determine the impedance looking into here. Well, what is the impedance looking into here? If I put a voltage source here, delta V, I want to know what delta I is. For I, right? So let's call this delta I. And delta V over delta I is basically my input impedance. So what is delta I? Well, delta I is determined by the voltage drop across this guy divided by the impedance. So what is the voltage drop? The voltage drop is delta V minus A delta V divided by Z. That's delta I. Correct? So this is, okay, so I have to keep it consistent. Let's call this AV, and let's say AV is negative. So then this becomes AV. And then this becomes delta V, 1 minus AV over Z. Therefore, Z in, so delta V over delta I is going to be Z divided by 1 minus AV. In general. Right? So it seems that if my gain is negative, if AV is negative, then what happens is that it tells you that it drops the impedance. Or in the case of a capacitance, so since capacitance, remember, capacitance, the impedance of a capacitor is 1 over CS, so it increases the capacitance. So it's 1 over that. So what's going on? Because basically you push this up, this goes down, you draw a lot more current. So this kind of the input looks like as if you have an impedance which is 1 minus AB Z. Or another way of writing it is 1 plus absolute magnitude of AB Z. So it becomes small. It looks, I'm sorry, 0 flat. It looks smaller. And you have your amplifier. So what's really going on? If you think about this impedance, think about this resistance as a long piece of, I don't know, carbonated, carbon bar. Right? This side of it is going up, and this side of it is going down. And this is this long piece of resistance. So as you move from this end, you see, so the movement up and down, the beginning is this much. And then when you get closer and closer, you get smaller. And then it goes in the opposite polarity. It becomes larger and larger. Right? So there's some point along this resistance at which there's no fluctuation. Because one side goes in the opposite direction of the other. That's basically the fulcrum of that lever, or like this point. Right? There's one point. If two opposite sides are going in opposite direction, there exists one point that doesn't move. So I will separate those two resistances and write it as 2. I can think about it as resistance. So let's call this resistance Z1 and this resistance Z minus Z1. So the overall resistance is still Z. Now, at this point, I choose it so that this doesn't move. So it's a virtual ground. Now, I want to find what Z1 is, because that gives me that virtual ground point. So what's the property of that virtual ground? It doesn't move. So it means that its potential is 0. Right? So if that's the case, then this current, so let's call it delta I, which is going to be the same here, times this resistance has to give me the delta V. So I know that delta V divided by this resistance or impedance Z1 is delta I, but then I have to have something else. This end moves by AV times Z, moves by AV times delta V. amplifier. But this voltage divided by this resistance also have to give me the same current because there's no other place for the current to go. So what is that voltage? That voltage, so this is 0, this is delta V. So it's minus AV delta V. It's this voltage minus that voltage divided by Z minus V1. So between these two, I cancel delta V, and then it allows me to solve for Z1 in terms of Z. So it says minus AV Z1 is equal to Z minus Z1. So I bring this one to the other side, so 1 minus AV Z1 is Z, therefore Z1 is Z over 1 minus AV. Which is what we had already determined. That's another way of looking at it, right? This is the same result as that. So it's as if you can, so if this node doesn't move, then would it care if I shorted the ground? No. So in this case, I have a Z1 to ground, and then I have some other element here, Z minus V1, but this has absolutely no significance with the conditions that I've defined, because it's in parallel with what? An ideal voltage source. Anything in parallel with an ideal voltage source, other than an ideal voltage source, is just the ideal voltage source. Right? So you can put it there, but it doesn't matter with respect to stuff. It's in parallel with an ideal voltage source. So that's C1. That's the way the impedance looks at the input. So this kind of thing leads people to think sometimes that, okay, well, what is the, so I'm going to show you the so-called Miller theorem, which is not correct. I'll tell you why it's not correct. So now, this was correct. What I just showed you is correct. So far. Okay. So here's how it goes. It says you have a network, multiple things attached to each other, and then you have an impedance somewhere in this network. So these are attached to other things, and these are attached to other things. Let's call this voltage V1, and let's call this voltage V2, and then let's call this Z. It says, okay, the current through this branch, I, is V1 minus V2 divided by Z. But if I could replace this Z with two impedances to ground, Z1 and Z2, and if I could force these currents to be equal, I and I, while this is V1 and V2, the rest of the network has no way of knowing that this has happened. Okay. And of course, when you make this assumption, so the current through here is V1 over Z1, which is I, and that current is V2 over Z2, which is also I, and I, which has to be equal to this I, V1 over V minus V2 divided by Z. So you can divide both sides by V1, all sides by V1 basically. Or let's take these two first. Divide both sides by V1. That's the gain, right? Presumably. So V2 over V1, we define that as A, the ratio of these two voltages. So this becomes 1 minus A, Z, and this becomes 1 over Z1. Therefore, Z1 is Z over 1 minus A. And you can do the similar thing for this between these two guys and divide both sides by again V1 or V2.
It has the minus sign to the V2 over Z2. No. Right. Yeah.
Oh yeah, this has to have a minus sign. Correct, thank you, because the current is going this way. Thank you. So if I take that, then I would see that Z2 becomes Z over 1 minus 1 over 1 over A. And then you say, great. So from now on, anytime I have like a stage like a common source or common emitter, I just basically take that capacitance 1 plus GM RC C mu here. And it seems that I will have a capacitance at the output, which would be what? It would be 1 minus 1 plus 1 over GM RC C mu. So according to the Miller theorem, quote-unquote theorem, these two are equivalent. Correct? What's wrong? Are these equivalent, first of all? Why not? Can you tell me, can you give me 1, 2, 3, as many reasons as you can why? Why they're not?
We just saw that it's not true. We just saw that it's not true because in this case the input impedance is just capacitive, but we saw that we have.
That's one thing. That's one way. There's some simpler way to see this. How many poles and how many zeros does this transfer function from here to there have? It has 1 0 and 1 pole, right? How many poles and zeros do we have here, do you think?
2 poles, no zeros.
You have 2 poles, right? Because you have 2 separate capacitors here that are not. And you have no zeros. Because nodding of these capacitors individually, shortening this or shortening that, both kills the gain. So you take it and you can verify that if you want. I mean, we haven't proven all of that yet, but you can verify in the case of KBL, that's just an obvious one. It took a stage with 1 0, one pole, one left half plane pole, and right half plane 0, turned it into a stage with 2 left half plane poles and no zeros. Therefore, this cannot be a theorem, as an example. What's wrong? Okay, so I told you that is correct, but this is wrong. And they gave the same result here, but that's what's the difference between these two? There are several things that are different. Go ahead. Go ahead.
Okay, I guess thinking out loud here. But in the first case, we said Z1 plus Z2 has to equal to Z, right?
Right.
Whereas we didn't do that on these. So,
I just forced the currents to be the same, for the same voltages in that point. There are several things that can go wrong with this guy. So I said, and kind of like I said it in the passing, and you may or may not have noticed one thing that I just said in the passing. I said, if you could draw this like this, there's no guarantee that there's an equivalent circuit like this for that. As an example, imagine a circuit that's only, the 2 parts of the circuit are connected only through this guy. Right? Just like have a big circuit on this side and a big circuit on that side, and then there's this 1 Z connecting the 2 sides. If you do this, they are completely separate. There's no way for them to communicate anymore.
Exactly.
So you may not even be able to do that to begin with. Let's assume you could. I mean, this is wrong on so many levels. It's just like, something fun to talk about. So then let's assume that you could. Then the way I wrote it, defined A, and this is another thing that I swept under the carpet. I defined A as a ratio of V2 over V1. But nobody said this is a constant. The ratio of 2 voltages can be frequency dependent, depend on all sorts of things. So now, if you want to really make it correct, if you could separate them, you have to make this a function of frequency to begin with. So all of these parameters that you have here will become frequency dependent too, which becomes completely useless, right? You have this frequency-dependent gain that gets multiplied by this like capacitance to force it to give you the accurate result. So, what's wrong? Now, in this picture, actually, this picture is probably the key to seeing what is wrong. See, when you have an ideal amplifier with 0 output resistance, this point exists. Or basically, for some non-zero output voltage, source resistance, sorry, non-zero source resistance. So there's no such thing as Miller's theorem. There's a Miller effect, which is what we discussed. This side goes up a little bit, that side goes up a lot. You get a lot more current drawn, and if you want to know the exact results, those are the exact results. The one that we derived using our first order transfer characteristics. Those are exact, there's no approximation. Fine. So that's my annual rant for regarding the Miller theorem. So now that we got that out of the way, let's talk about some other useful things.
Can I ask a quick question?
Sure.
What happens if the gain in that picture is not negative?
Oh, that's what I was going to talk about next.
Okay.
The check is in the mail. I planned this question. Okay. Okay, so that's a good question. So what happens if the gain is not negative? What if the gain is positive? So the gain is positive means that this side goes up, that side goes up too. Let's start talking about it when this side. First, let me ask you. Let's ask you a special example about a special case. Let's say the gain is +1. What that? The gain is +1, which means that, and if this were an ideal amplifier, well, so this is a negative gain, right? This is the gain of +1. This being the input, that being the output, right? What is the voltage that the impedance or the capacitance or whatever you have experiences? 0. But what is the current it draws? 0. So what is the significance of this element? It's completely insignificant. You can take it out. It's a branch that draws no current. So you can replace it with an open circuit. So it's not there. It just disappears. By the way, that goes back to something that I may have just erased. Oh, I did erase it. You remember in the source source follower, the counter emitter with the C pi? You remember I said both the pole and the zero have very high frequency. One way to see that is that the capacitance is sitting across something that has a gain close to 1. Sitting between the C pi was sitting between the input and output, right? So this side of it goes up and that side of it goes up. So the C pi sitting between those input and output doesn't experience much current, so it doesn't do much. So the frequency is not limited by that, really. Now, what if the gain is a little less than 1? What does it look like? That's going to be a little trickier to produce, so I'm going to do that. This is again a little less than 1. So both of them go up and down, but you see less of a swing. Right? If the gain were 0, this is what you see. So whatever the swing you have at the input, that's the cross thing. Now this reduces the swing, so the impact is reduced. So, and you can see this, right? Or for the capacitance, for the impedance is increased, meaning that it's a larger resistance or larger impedance. So if A is positive, then it makes the impedance larger. Right? And if A is 1, it becomes infinity, it becomes an open circuit. Right? Okay, no. What if it's greater than 1? Now that's fun. So from the equation you can see something, right? So by the way, in those cases, what you see, when you go to those cases, then Z, so let's think about what happens to this threshold run still exists, right? But this resistance has to become negative, right? This has to become a negative resistance. So what happens is that when you do this, then this guy has to become negative. Meaning, so if the gain is greater than 1, it means like, it's like something like this. Right? That's what gain greater than 1 means. And so you push this side up, that side goes this direction. So you increase the voltage, it's an element, when you increase its voltage, it gives you more current. The more you increase its voltage, the more current it sends back to you. That's a negative resistance, negative impedance. So you can create negative impedances this way. Now, you can actually create negative capacitances, which are also interesting. I mean, if this is a capacitor and you have positive gain greater than 1, you can create negative capacitance. I will talk to you about it maybe next time, a little bit more, show you an example of how you can make it. Let me just show the example now, and then we can talk about it a little bit more. It's a simple example. So, how do I make I need an amplifier. I need to create a equivalent capacitor across something that has a gain greater than 1, but non-inverting gain. What stage does that? Does my common emitter do that? I can do it across common base. That's one way to do it. But it creates another 0, which is not fun. A typical way of doing this, a practical way, is using a differential amplifier. Now, in the differential amplifier, as long as you're driving differentially, you have access to both inverting and non-inverting nodes, outputs, right? So if I start from here and look at there, this one goes up, this one goes up too, by some gain. And this one goes up, that one goes up too. And the gain from here to there is the same as the gain of the differential amplifier. So I could connect a capacitor across here, and another one across here. Now if I do that, if I have gain, this voltage goes up, this voltage goes up more. And this voltage goes down, this goes down more. So I can create a negative differential capacitance here. You can actually use this to compensate some of your positive capacitance. But you gotta be careful not to go overboard, because once you start doing it and you have multiple capacitors, you have to really do the full analysis, which you can later on, once we understand how to do multiple capacitance analysis. And you will see at some point there will be some other poles and zeros. So you will gain some in the beginning, but if you push it really, really hard, then you may get things that you didn't expect. For instance, it can become unstable or not improve at all. But yes, it does improve. This is a known technique called neutralization. You neutralize the intrinsic parasitic capacitance of the device by adding extra capacitance. So this is an example where you see adding capacitance is not necessarily making things worse. These capacitances, you can have the stage without this capacitor and with this capacitor. You see it performs better with the capacitor. So it's not true that you even adding a capacitor